The next reaction of the alcohols is their oxidation. It's a very important reaction because due to this reaction we are able to prepare aldehydes and ketones and even carboxylic acids. Now what we need to know is that the alcohols can be oxidized by using many oxidizing agents. So the oxidizing agents generally used are the PCC, which is called pyridinium chlorochromate, which is CrO3.C5H5N.HCl. That's a very useful oxidizing agent, as it oxidizes only the primary alcohols to the aldehyde, secondary to ketones, and no action on tertiary alcohol, and it prevents the further oxidations of the aldehyde and ketone formed to the corresponding acid. So if we want particularly only the aldehydes and ketones, this is the best reagent. We can also use chromic anhydride under anhydrous conditions, which also oxidizes primary alcohols to aldehyde, secondary to ketones, and no action on tertiary. Now these oxidizing agents exclusively gives us aldehydes from the primary alcohol and ketones from the secondary. Whereas if we are using the stronger oxidizing agents like KMnO4 H2SO4 or K2Cr2O7 H2SO4 or KMnO4 in basic medium called Bayer's reagent, they can also show the same type of oxidation. But the problem with these strong oxidizing agents is that they oxidizes further the aldehyde formed to the corresponding carboxylic acid. Therefore, if you want aldehyde, they have to be distilled out immediately as they get further oxidized. In ketones, what they do is, yes, ketones further oxidation is a little bit difficult, but what we do is, if we heat them, yes, we can get acids. Let us see now how they are used. Let us take the example. If we have a primary alcohol and we are using any one of these, K2Cr2O7 or KMnO4 in acidic medium, first we get is an aldehyde, ethanol. So ethanol gives ethanol, which gets further oxidized in the same reaction mixture to the corresponding ethanoic acid. This is of 2 carbon, this is of 2 carbon, and this acid is also of 2 carbon. That's the major problem. Whereas if we are doing its oxidation by PCC, we only get aldehyde and no further oxidation is possible. That's the best use of the PCCs. Let us take now ketones, secondary alcohols, how we get ketones out of that. Now let us see how a secondary alcohol is oxidized. If we are using the same strong oxidizing agents like K2Cr2O7 in acidic medium, KMnO4 in acidic medium, the first thing which we get is a ketone out of it. So we get ketone or a propanone out of this isopropyl alcohol. Now what happens is, its further oxidation in the same medium is a little bit difficult. The reason is it doesn't have any CH bond. That is why if we heat it, then only the potassium permanganate in acidic medium will be able to oxidize what? This ketone, and this results in the breaking of a CC bond, one of the CC bond breaks, and what we get is the corresponding carboxylic acid of the two carbon parts which we get. So one carbon part obtained from this is of 2 carbon, so we get ethanoic acid, and one part we get of 1 carbon, which is called methanoic acid. So we get ethanoic and methanoic acids respectively. That's the most beautiful thing about this is, but you need to know this, that this breaking of the CC bond or the oxidation of ketones, if the ketone is unsymmetrical, follows a Popoff's rule, which says that the carbonyl group goes with a smaller chain. So, but that you will learn later on in the cases of the aldehydes and ketones. But what you need to understand now in this case is that yes, ketones further oxidation to acid is possible, but that only happens when we take KMNO4 in acidic medium and we heat it, then only the CC bond breaks. Otherwise, the further oxidation of the ketones to acid is not actually possible in normal conditions. Now let us see how, and I have to tell you one more thing, that in this case, if we have used PCC, the pyridinium chlorochromate, then what would have happened is we have got only the ketones, and that is why we prefer to use this one rather than going into so much of details. So PCC also gives us the same propanol. Now let us see the tertiary one. In case of tertiary alcohols, what we find is, since tertiary alcohol has no CH bond at the alpha carbon, which is having the OH group, so its no oxidation is possible. So no oxidation. If we want to oxidize it, remember we have to use what? KMNO4 in acidic medium along with heat, which results in the breaking of one of the CC bonds. This will give us what? A ketone, which and the carbon part which gets separated out gets converted to its acid, whose further oxidation, if possible, can also be done. But under normal conditions, its oxidation is not done. We can do the oxidation of alcohols catalytically also. And so let us see catalytic oxidation. In this, what we do is primary alcohol is oxidized to aldehyde by passing its vapors from copper at around 300 degrees Celsius. So it gets converted to the aldehyde because dehydrogenation takes place. In a very similar way, if we have a secondary alcohol, when passed through what? Copper at 300 degrees Celsius, what we get is it gets oxidized to what we have is called propanol. And very similarly, if we have a tertiary alcohol with copper at 300 degrees Celsius, it shows dehydration and gets converted to an alkene rather than showing what? The oxidation. So that's the basic difference. Yes, we can prepare aldehydes and ketones from primary and secondary alcohols catalytically also. Now let us see the chemical reactions of phenol. The most important chemical reactions of the phenol we can say is its electrophilic substitution reactions. We know that the OH group attached to the benzene ring is having what? 2 lone pairs on the oxygen. As a result, which gets easily being transferred to the what? Benzene ring, and therefore what we find is that the OH group is showing what? Plus R effect, and as a result there is a high electron density at ortho and para positions. These are the resonating structures which we get out of it. It is like this. So we have seen in these 5 resonating structures that the lone pairs of the oxygen has taken a complete round of the benzene ring and they are back on the oxygen. And as a result, because of this, there is a high electron density at ortho and para positions. So therefore, due to their plus R effect, they are ortho and para directing. So they are ortho-para directing, which means whenever we'll be doing electrophilic substitution, that will be taking place at ortho and para positions. And since they are giving electron to the benzene, they are called ring stabilizing groups. So it's a ring stabilizing group. It increases the reactivity of the benzene by introducing a negative charge, and that is what we see. Now let us see its different electrophilic substitutions. The first one, let it be nitration. What is more important to know is that since it's a ring activating group, we don't need harsh conditions for electrophilic substitution reactions. They can take place very easily on their own. That's the major thing is. So when we take phenol and we treat it with dilute nitric acid, what we get is both orthonitro and paranitrophenol. This is paranitrophenol, which is a major product along with, of course, water, and this is the minor product. But yes, it's not formed in a very small amount. It's again is formed in a good amount. The reason being is it has what? Intramolecular H bonding. As a result, what we find is this becomes steam volatile, whereas this is able to form hydrogen bonding with the rest of the other molecules. That is why what we find is, yes, we find that it is very having higher boiling points. So we get both ortho and para products, whereas para one is found, of course, more than the ortho one.